we have completed the physical and chemical properties of the phenols. And in part 4, today we are going to study about the ethers. Okay, so what are the ethers? Let us start from today's class. Yes, so what are ethers, ma? Ethers means the functional groups which are having ROR. ROR functional group is called as ether. So ether means ROR. ROR functional group where R and R prime are alkyl or aryl groups. So ethers are formed when a hydrogen atom in hydrocarbon is replaced by the alkoxy or aryloxy group. So alkoxy group means nothing but RO group. R prime O. Here R may be aromatic also, C6H5. That means your benzene ring. If that is aromatic means that will become aryloxy, because aryl means benzyl ring. Okay, phenyl ring you are calling. So that means if the hydrogen of that alcohol is separated, that means here if you think that that is hydrogen means that is alcohol, ROH is alcohol. If this hydrogen is replaced by the alkyl group, okay, then replaced by alkoxy group or the aryloxy group, then you are calling it as the ethers. So here ROR is the main functional group for the ethers. Oxygen on either side of the oxygen, alkoxy and aryloxy groups will be present. So let us see what are the examples for the ethers. So here comes the examples. CH3 is OCH3. CH3 means methyl and another methyl. On either side of this oxygen, you are having the methyl. So methyl 2 times it is there. That's why dimethyl ether. So the compound name is dimethyl ether. So this is one of the compound for ether. Okay. Another example for ether is diethyl ether. So see here. Ethyl methyl ether. See here. CH3 CH2 is your ethyl functional group, ethyl alkyl group, right? And CH3 group is methyl group. CH3 is methyl. So here, according to the IUPAC system, E will come first in the alphabetical order. That's why the name of this example will be ethyl methyl ether. Yes, the name of this compound is ethyl methyl ether. Okay, so in this way, these are some of the examples of the ethers. So let us study in detail. There are some types of ethers, that is symmetrical ethers or unsymmetrical ethers. In the next slide, we are going to study about those symmetrical and unsymmetrical ethers. Yes, here ethers, they are classified into two types, that is simple or symmetrical ethers. Okay, so what are these simple or symmetrical ethers? Symmetrical, in this word only it is indicating. Symmetrical means same alkyl groups. If they are present on both the sides of the oxygen atom, then they are called as symmetrical ethers. So let us look forward for the definition. Yes, here comes the definition. If two alkyl or aryl groups are attached to the oxygen atom are the same, if the attached alkyl or aryl groups are same, then the ethers are called as simple or symmetrical ethers. So let us understand with this example here. See here. Here we are having oxygen at the center. On either side of oxygen, here you are having your methyl group. Okay, so this is our methyl group. So on both the sides, we are having same methyl groups. So both the sides, same number of carbons are there. Here one carbon alkyl group, here also one carbon alkyl group. That's why it is coming under symmetrical. That means on either side of the oxygen atom, the alkyl or allyl groups should be same. Methyl means here also should be methyl. If it is ethyl here, C2H5, then here also it should be C2H5, diethyl ether. So like dimethyl ether is an example for symmetrical ether. Why? Because they are same on both the sides of the oxygen atom. Okay, right. Next example, let us see. Here comes diethyl ether. See here, CH2CH3 is which group? This CH2CH3 group is the ethyl group. So both the groups are ethyl. Sorry, ma, here it is not CO. It is only oxygen. Only oxygen, ma. Only ether functional group. On either side of the oxygen groups, we are having two ethyl groups. Both are same alkyl groups, ethyl groups. That's why it is also coming under symmetrical ethers. And the name will be diethyl ether. Di, two times. Two times ethyl groups are present. That's why diethyl ether. So these are the examples for the symmetrical ethers. Okay. Now, in the next slide, let us study about the unsymmetrical ethers. They are also called as mixed ethers. So what are unsymmetrical ethers? If two alkyl or aryl groups attached to the oxygen atom are different, here in the previous symmetrical, they were same. In unsymmetrical, they are different. Then the ethers are called as mixed or unsymmetrical ethers. So let us see the examples here. Here, CH3 is the methyl group, right? And on the other side of the oxygen, here you are having ethyl group, right? So that means these two groups, ethyl and methyl, these are two different alkyl groups. So that's why it is coming under unsymmetrical ethers. So when you look for the naming, E will come first, ethyl, methyl, ether. That's why the name is ethyl, methyl, ether. Now let us see next example for the unsymmetrical ethers. Yes, here C2H5 and C6H5 is there. Ma. C2H5 is which alkyl group? Ethyl alkyl group, right? Ethyl alkyl group. What is C6H5? C6H5 is your phenyl because C6H6 is our benzene. So from benzene, if you are removing one hydrogen, that will become phenyl. So here on either side of this oxygen, you are having one ethyl group and another phenyl group. That's why the name of the compound is ethyl phenyl ether. Ethyl phenyl ether. Because according to IUPAC system, E will come first in the alphabetical order. Ethyl phenyl ether. So these are the unsymmetrical ethers. Okay. Now let us study about the structure of the ether. So in the ether structure, you are having the oxygen atom. On either side of the oxygen atom, you will be having the alkyl groups. So here we are taking CH3 methyl group. On another side, also we are taking the same CH3 methyl group. So that means here, same like your water molecule only, ether also is having the same structure. That is, the shape of the water molecule is what? V shape, right? V shape or butterfly shape. The water molecule shape is butterfly shape. Already we have studied. And or bent shape also we are calling bent shape. So all these are the different shapes for the water molecule. In the same way, ether is also having the same shapes because in the water molecule, there are two lone pair of electrons on the oxygen atom. In the same way, for ether also, there are two lone pair of electrons. Two lone pair of electrons are present. That's why its shape and geometry will be resembling to the water molecules. Okay, when you look at the bond length between the oxygen and carbon, the bond length is 141 picometers. Then what is the bond angle? Let us see. The bond angle for the ether is 11111, that is 111.7 degrees. Okay, so this is the bond angle for ethers. So here In ethers, the 4 electron pairs, that means here 4 electron pairs means 4 electrons. Actually, it is 2. 2 electron pairs on oxygen are arranged approximately in a tetrahedral arrangement. In water, it was also a tetrahedral, that is sp3 hybridization. The oxygen is undergoing sp3 hybridization. sp3 hybridization means what is the expected geometry, ma? Tetrahedral. Okay. So for water, it was tetrahedral. Here for ether also, it is also tetrahedral. But there is a deviation from this tetrahedral geometry. So why there is a deviation? Because of the presence of these 2 lone pair of electrons. These 2 lone pair of electrons are changing the geometry from tetrahedral shape to V shape or butterfly shape or dent shape. Okay, so that's why the geometry is different from tetrahedral to V shape because of the presence of these 2 lone pairs. Here, the lone pair repulsions and lone pair bond pair repulsions will be causing the deviation of this tetrahedral shape, and also the bond angle for tetrahedral, what you'll expect, it will be 109 degrees, 28 minutes it should be. But because of this presence of these 2 lone pairs, the bond angle is also is deviating from 109 to 111.7 degrees. Okay, so the bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the 2 bulky RR groups. These bulky RR groups, alkyl groups, they are repelling each other. Because of that reason, the bond angle is increasing and the bond length is 141 picometers, is almost same as in the alcohols. Okay, so this is the structure of the ethers. Yes. Now let us study about the preparations of the ethers. So what are the preparations of the ethers? So how are you preparing the ethers? So preparations, first preparation is by dehydration of alcohols. From the dehydration of alcohols, we can prepare the ethers. So let us see. Alcohols are heated with concentrated H2SO4 at 413 Kelvin temperature to form the ethers. Right? Here, alcohols on heating. Suppose if you are taking ethyl alcohol on heating at a temperature of 413 Kelvin, at a temperature of 413 Kelvin, and in the presence of H2SO4, ethyl alcohol will undergo dehydration. Dehydration means what? Removal of water molecule. Okay, ma. When you are removing the water molecule, you'll get the ether. Okay, see here, ether water molecule is eliminated. So let us see the mechanism, how it is occurring. See here, if you are taking CH3 and CH2, CH2, OH, OH I am writing here now. Okay, that is 1 mole ethyl alcohol. Again, another ethyl alcohol if I am taking. So instead of this CH3, I am writing here CH2, CH2, and one of the hydrogen I am writing here down, right? And remaining CH2, CH2OH. Yes, just a minute, ma. See here, ma. In CH3, CH2, OH plus another molecule of CH3, CH2, OH. From both these molecules, if you are removing one hydrogen from here and OH from here, so what is left over? See here, CH3, CH2O, CH3, CH2O. Remaining is what? Again, CH2, CH3, CH2, CH3. That's why you are getting the remaining product as ether. Okay, so simply removal of the water molecule, remove the water molecule, then you'll get the desired ether. You can get your desired ether. Okay, so that is first preparation of ether by the dehydration of alcohols only in the presence of concentrated H2SO4 and at a temperature of 413 Kelvin. Okay, ma. So this is the first preparation of ether. Yes. Now let us move on with the second preparation of ether. So second preparation of ether is Williamson synthesis. This is very, very famous, ma. This is an important VSAQ question. They are asking for VSAQ question for 2 marks. 2 marks VSAQ question, it is important, ma. So in the Williamson synthesis, when an alkyl halide is treated with sodium alkoxide to form an ether, this reaction is known as Williamson synthesis. Let us see with the example here. Here, alkyl halide Rx is the alkyl halide, R prime ONA, okay, that is sodium alkoxide. Sodium alkoxide, RO is alkoxide. Sodium alkoxide, when you are taking, just to simply remove this halogen and sodium. So what is left over? R O R prime, R O R prime, remaining NaX is eliminated. So this is the Williamson synthesis, ma. Okay, ma. Again, you'll be having this method is used for the preparation of both symmetrical ethers and unsymmetrical ethers. We can take here R groups, both same methyl or ethyl groups, or one methyl group and another ethyl group also we can take. So let us study in detail what is the Williamson synthesis for symmetrical and unsymmetrical ethers. Yes, what is the Williamson synthesis for symmetrical ethers? So ethyl iodide is treated with sodium ethoxide to form the diethyl ether. Okay, so that means, see here in this example, you can see here, ma, ethyl iodide here you are taking, and ethyl sodium ethoxide, NaC2H5O, Na, ethyl iodide and sodium ethoxide. So these alkyl from here, NaI, just to simply remove the sodium and iodine. Sodium and iodine you remove, NaI, and remaining is C2H5O, C2H5. C2H5O, C2H5. This is your ether, ma. Here C2H5 is ethyl, and here also C2H5 is ethyl. Both are similar ethyl groups. That's why it is diethyl ether. Okay, ma. So this is the example for symmetrical ethers. Okay, ma. So Williamson synthesis for symmetrical ethers are ethyl iodide. When you are treating with sodium ethoxide, simply remove the removal of that sodium and halogen from that alkyl halide. If you remove, simply you'll get the ethyl ether. Okay, diethyl ether. Okay, so that is the example for the symmetrical ethers. Then let us see the example for unsymmetrical ethers. So here comes the example for unsymmetrical ethers. So Williamson synthesis for unsymmetrical ethers. Best yields of unsymmetrical ethers are obtained when alkyl halides are primary. When you are taking primary alkyl halides, this is very, very important. When you are taking primary alkyl halides, and alkoxides are tertiary, and alkoxides are tertiary. Alkoxides are tertiary. Yes, ma'am. So here we are taking here alkyl halides. Here CH3CONA is the primary tertiary alkoxides, ma, because this carbon is the tertiary carbon. This carbon is our tertiary carbon. So here we are taking tertiary alkoxide, and Here we are taking primary alkyl halide. Here we are taking bromine is attached to primary carbon. So primary alkyl halide, when you are taking, then simply remove of this sodium and bromine. Removal of the sodium and bromine. Then you'll get remaining is what? CH3, 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 CO, CH2, CH3, CH2, CH3. That is NaBr. So in that way, we are getting the alkyl halide. Okay, sorry. In that way, we are getting the ether. So that is tertiary butyl ether. Ethyl ether. So this total group is butyl group. కొంచెం సౌండ్ చేయకుండా చేసుకోరి ఫాతిమా. Yes, tertiary butyl ether. Okay, so this is the tertiary butyl group, and here is your ethyl group. Ethyl group. So tertiary butyl ethyl ether. Okay, so this is the preparation, Williamson synthesis preparation for unsymmetrical ethers. Okay, now let us move on for if the alkyl halides are tertiary and alkoxides are primary. What are the products, expected products? Let us see. In the next example, we can see there here. Yes, here both are unsymmetrical only, but here we are taking tertiary alkyl halide. Instead of primary alkyl halide, we are taking tertiary alkyl halide, and sodium alkoxide we are taking here primary. Okay, there we are taking tertiary alkoxide, but here we are taking primary sodium alkoxide to form the alkene, and no ether is formed. That means, see here, for tertiary alkyl halide, CH3CBr plus NaOCH3. CH3CBr. How many groups are there totally? Tertiary butyl. Okay, this is your tertiary carbon. Tertiary butyl bromide. When you are treating with the primary sodium methoxide, here it is your primary carbon. Okay, so primary, when you are taking, just simply removal of this tertiary butyl bromide, what you are doing? Remove the NaBr. Okay, right. Now next, from this hydrogen, here O and hydrogen from here, oxygen, and out of these three hydrogens, one hydrogen you remove as OH, and one hydrogen from here you remove as H. So when you are removing as H2O here, then you will get only CH3C double bond CH2. So let us see that example in detail, mechanism. So simply, first you have to remove the NaBr, right? First remove the NaBr. Okay, then CH3O is left over. From this CH3, we are taking we are writing the CH3 as CH2H. So similar. Now I am removing CH3OH. CH3OH. This is our methyl alcohol, and remaining is what? CH2. And here, because of this bond and here this bond, here it will forming double bond CH2. Remaining CH3, 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 and double bond CH2. Another CH3 group is present as it is on the group. Yes, both the methyl groups are present. Instead of this CH3, you are getting here CH2. Why? This hydrogen from this methyl group has been taken over by this methoxy group, CH3OH, methanol. That's why you are getting the alkene here. Okay, so that means if tertiary alkyl halide, if you are treating with sodium alkoxide, then you are getting we are not getting the ether, but you are getting the alkene here like this, and methyl alcohol you'll be getting. But if you are taking primary alkyl halide, means you'll get the ether there. That is the difference, So remember this point, because they may confuse you for your objective, IIT, MSET or NEET, Okay. Then Next comes the physical properties of the ethers. So what are the physical properties of the ethers? The first physical property is the CO bonds in ethers are polar and thus have a net dipole moment. Okay, they are polar in nature. Okay, polar means they are slightly positive and negative in nature. Then second physical property is due to the absence of hydrogen bonding. In ether, there is no hydrogen bonding. Hydrogen bonding is absent. Boiling points of ethers are lower than those of alcohols and phenols. And lower ethers are soluble in water. Very, very important point, ma. Lower ethers, that means methyl, ethyl ethers, like that, those are soluble in water due to hydrogen bonding with water, but the solubility decreases as the molecular mass increases. So what are the examples here? So here, lower methyl ethers. So that is ROR. Here we are taken ROR is the ether. So how they are soluble in water? Let us see. Here we are taking the water molecule. Yes, this is the water molecule. So, and another water molecule also we can take here. Yes, here we are taking two water molecules. This ether, it will be forming the hydrogen bonding with this hydrogen, okay? And this hydrogen also, it is forming intermolecular hydrogen bonding. That's why it is soluble in water. This is possible only for the lower ethers. That means for methyl ethers and ethyl ethers, okay? So let us see what is that hydrogen bonding. See here, we can see here the hydrogen bonding. Because of the formation of this hydrogen bonding, only in the lower ethers they are soluble in water, but higher ethers they are not soluble in water because of the higher molecular mass of the alkyl groups. Okay, so these are the physical properties of the ethers. Now, next let us see about the chemical reactions of the ethers. So what are the chemical reactions of the ethers? Yes, first chemical reaction is cleavage of CO bond in ethers. So the cleavage of CO bond in ethers, it will be taking place only with the excess of hydrogen halides. That means the hydrogen halides, they should be taken in excess. Dialkyl ethers react with excess hydrogen halides to form two alkyl halides molecules. Okay, so let us see here. ROR plus HX, when they are reacting with excess of hydrogen halide, what is happening here? Simply OH, ROH, it will be forming as alcohol, and remaining RX will be forming as alkyl halide. Now again, this alcohol in turn, it will react with one more mole of hydrogen halide to give rise to alkyl halide. RX, it will give rise, and removal of water molecule, removal of water molecule. So in that way, they are giving you 2 moles of alkyl halides, two alkyl halide molecules they are giving because of the cleavage of CO bond in ethers. That's why, because of this reason, they are taking place in the excess of hydrogen halides. Okay, ma. So this is the first chemical reaction of ethers. Now, one alkyl aryl ethers react with hydrogen halides. Alkyl oxygen bond is cleaved due to more stable aryl oxygen bond to form phenyl and alkyl halide. So let us understand this with an example. Here, C6H5 phenyl ether you are taking. Okay, so in this phenyl ether, simply you remove the RX, R and X alkyl halide. If you remove means you are getting the phenyl alcohol. That is phenol. We are getting the phenol. Okay, ma. So this is reacting with the hydrogen halides. Here, the bond is broken between alkyl and oxygen. Alkyl group means nothing but the carbon. Between the carbon here and the oxygen, the bond is broken. So that's why they are coming under the cleavage of CO bond in ethers. Okay, so these are the first chemical reactions of ethers. Now, let us see the second chemical reactions of ethers. So what are the second chemical reactions of ethers? So here, unsymmetrical ethers, they will react with hydrogen halides to form the alcohol and alkyl halide. Alkyl halide and alcohol will be formed. In this reaction, the lower alkyl group forms the alkyl halide. See here, we can understand with this example here. Here, ethyl CH2, CH3 group is ethyl, methyl, ether. These are the unsymmetrical ethers only. So unsymmetrical ethers, when they are reacting with this hydrogen halide, the lower alkyl, okay, so that means here CH3 is the lower alkyl. It will form the alkyl halide, that means CH3I, like this. Okay, it will give rise to CH3I. Yes, see here, CH3I, because the lower alkyl group is reacting with the halide. CH3I, methyl iodide is formed. Then, what is left over? CH2, CH3O, CH3, CH2O, and hydrogen from this hydrogen halide. They will react to form alcohol. They will give you alcohol, CH3, CH2OH, ethyl alcohol. Always the lower alkyl will be forming the alkyl halide and the higher alkyl will be forming the alcohol. Remember this point. And in this way, here also if you are taking ethyl, methyl, ether and we are reacting with 2 moles of HI means here we are getting methyl iodide and ethyl iodide. If you are taking 2 moles of HI, excess HI, then instead of alcohol OH, here we are getting ethyl iodide by the dehydration mechanism, by the removal of water. Dehydration means removal of water. So that means both iodides only you will get when you are taking excess of hydrogen halides. Remember this point. Limited hydrogen halide, if you take lower alkyl group will form methyl iodide, that is alkyl halide, they'll form higher alkyl group, they'll form the alcohol. But excess hydrogen halide, if you are taking means they'll form methyl iodide and ethyl iodide. Both iodides they'll be forming. Okay, so these are the preparations. These are the second chemical property of the ethers. Yes. Then let us see about the electrophilic reactions of the ethers. This halogenation means nothing but the electrophilic substitution reactions of the ethers. That means only electrophile will be attacking at the ortho and para position. So anisole undergoes bromination with bromine in ethanoic acid to form ortho and para broma anisoles. Para isomer is obtained in 90% yield. Para is obtained in high yields. So what is anisole means? Simply for phenol you are having OH. If this OH is replaced by CH3 group means OCH3 on the benzene ring, OCH3 group is present, that is methoxy. CH3 is methyl. O means oxy. Methoxy group is present on the benzene ring means that is called as anisole. Okay, on the benzene ring, if OCH3 group is present means that is called as anisole. So for the anisole, simply if you are doing bromination in the presence of ethanoic acid or acetic acid, any acid you can take, then at the ortho position and the para position, simply bromine will be substituted. Bromine is the incoming nuclear electrophile here. Okay, so let us see this example here. See here. Here we are getting the bromine at the para position, right? So at the para position, you are getting the bromine. And at ortho position also, you'll get the bromine. Yes, ortho position also bromine. But para bromo anisole is 90% majority, major product. And ortho bromo anisole is minor product. Okay, so these are the halogenation electrophilic substitution reactions of the ethers. Anisole. Anisole is ether only now. See here. This is the benzene ring and this is the methyl group. On either side of the oxygen group, they are the alkyl groups. Okay, so that's why this anisole is undergoing the halogenation. At ortho position, bromine or para position, bromine. Okay, So para will be 90%. Then ortho. Ortho is minor product. Yes. Let us look forward for the next electrophilic substitution reaction of ethers. So second electrophilic substitution reaction of ethers is Friedel-Crafts reaction. So Friedel-Crafts reaction means here Friedel-Crafts reactions we are having two types, that is Friedel-Crafts alkylation and Friedel-Crafts acetylation also you are having. So first we'll study about Friedel-Crafts alkylation. Anisole, when it is reacting with methyl chloride in the presence of anhydrous AlCl3. What is this anhydrous AlCl3? That is a Lewis acid. Anhydrous AlCl3 you can take, or you can take FeCl3 also. FeCl3 is also a Lewis acid. So always Friedel-Crafts reaction will be occurring only in the presence of this FeCl3 and anhydrous AlCl3. Whenever you look at the word Friedel-Crafts reaction means, you remember this point, it will take place only in the presence of Lewis acids. What are the Lewis acid? FeCl3 or anhydrous AlCl3. Okay, ma. So this is also a very, very important question for your 2 marks BSAQ question, ma. 2 marks. You will get 2 marks from this point. Okay. They'll ask you especially Friedel-Crafts alkylation and Friedel-Crafts acetylation. Alkylation means simply at the ortho position alkyl group or para position alkyl group. Let us see with this example. See here, anisole OCH3 on the benzene ring means anisole. When you are treating with methyl chloride, simply removal of this chlorine. Okay, ma. Removal of this chlorine and hydrogen from here, ortho position, add here methyl group, HCl will be lost. Okay, ma. So in that way, you can get here. See here is the 2 products, ma. Then at the ortho position, methyl group is substituted. Yes, at the ortho position, methyl group is there. That's why 2-methyl anisole, because this total is anisole. And at the second position, methyl group is there. That's why 2-methyl anisole, or also we can call it as 2-methoxy. Here, 2-methoxy toluene, because this total group is toluene. On benzene ring, if CH3 group is present, that is toluene. 2-methoxy toluene. Okay, ma. So here we can call it as 2-methyl anisole or 2-methoxy toluene at ortho position. If alkyl group is substituted at para position, that is 4-methyl anisole or 4-methoxy toluene. So that means here both ortho and para positions you are getting. Okay, ma. So para methoxy toluenes you are getting in the presence of which Lewis acid, that is FeCl3 and AlCl3. Okay, so that is Friedel-Crafts alkylation. Simply you are adding the alkyl group either at ortho position or para position. You are substituting electrophilic substitution reaction. Okay, ma. So these are the Friedel-Crafts alkylation reactions. Then we look forward for the Friedel-Crafts acetylation. This is also important for your 2 marks. So combinedly, they may ask you both 1 mark each or 2 marks for each. Okay. So Friedel-Crafts acetylation, acetyl chloride, that means CH3CO group is called as acetyl group. Okay. So anisole reacts with acetyl chloride in the presence of anhydrous AlCl3 to form orthomethoxy and paramethoxy acetophenones. Acetophenones you are getting here, ma. Okay, so see here, ma. Anisole, when you are treating with acetyl chloride, CH3CO, Cl, this is your acetyl chloride in the presence of AlCl3, that means your Lewis acid. Then at the ortho position, COCH3, just you are substituting, or para position, you are substituting COCH3. This is called as, that means when you are, this total group is called as acetophenone. Total group is called as acetophenone. On benzene ring, if COCH3 is present, means that is acetophenone, and OCH3 is methoxy group. At second position, 2-methoxyacetophenone is there. And in this product, here is the major functional group. 2, 3, 4. Fourth position, you are having methoxy group. That's why 4-methoxyacetophenone. Okay, so that means simply substitution of this CH3CO and this Cl and one of the hydrogen at ortho position or para position, they'll be eliminated as HCl. Simply substitute with this electrophile CH3CO, then you'll get the corresponding acetophenones. Okay, ma. So this is the Philograms acetylation. Yes. Next, we'll see about the nitration of the ethers. So this is the last reaction of the ethers. Anisole reacts with a mixture of concentrated HNO3 and concentrated H2SO4 to form the mixture of ortho and para nitroanisoles. So what is this concentrated HNO3 and concentrated H2SO4? This is our nitrating mixture. Already we have studied. So this concentrated HNO3 and concentrated H2SO4 is called as nitrating mixture. Nitrating mixture you are calling. So always nitration will occur only in the presence of this nitrating mixture. So it will give you ortho and para nitroanisoles. So anisole, your benzene ring with OCH3 group. When you are treating with this HNO3 concentrated and concentrated H2SO4, then you will get the anisole, and at ortho position nitro group will be substituted. See here, nitro group is substituted at ortho position 2 nitro anisole, because this is the second position, second carbon, 2 nitro anisole, and also you are getting para nitro anisole at the fourth position. You are getting para nitro anisole, okay, or 4 nitro anisole. Okay, so here ortho position is the minor product. Ortho is the minor product and para position is the major product. Para position is the major product. So these two are the products formed when the alkylation, nitration of anisole is occurring. Okay, so anisole reacts with a mixture of nitrating mixture to form a mixture of ortho and para nitro anisoles. So it will form ortho nitro anisole and para nitro anisole. Okay, ma. So here para nitro anisole is major product and ortho nitro anisole is minor product. Okay, so these are the chemical reactions of the ethers. Ma. Yes, here we have studied all these properties. Ma. Just a recollection, I am repeating here. Ethers means what? Which group? Ma? Here just we are revising here. Ma. So ethers means ROR group are called as ethers. So dimethyl ether or ethyl ether. Okay. So dimethyl ether is a symmetrical ether because both are the methyl groups, and ethyl methyl ether is the unsymmetrical ethers because on either side of this oxygen, here is ethyl group and here it is methyl group. That's why it is unsymmetrical ether. Okay. So once let us go back to this Williamson synthesis also. It is a very, very important question for their IP point of view. An alkyl halide, when it is treated with sodium alkoxide to form an ether, okay, this reaction is known as Williamson synthesis. Simply, alkyl halide you are treating with the sodium ethoxide, R prime ONA. Then you are getting ROR prime, okay, by the removal of NaX, that is sodium halides. Then you are getting the ether. Okay, so this method is very, very useful for the preparation of both symmetrical and unsymmetrical ethers, ma. So both symmetrical and unsymmetrical ethers you can prepare here. Okay, ma. Then let us see what is the symmetrical ethers preparation. Ethyl iodide, when you are preparing with treating with ethyl sodium ethoxide, both in both these compounds, ethyl group is present. Both are ethyls means symmetrical ethers. See here on either side of the oxygen group, both are ethyl groups. That means simply removal of this sodium and iodine, NaI, then you'll get the ethers. Simply remove the sodium halides, then you'll get the ethers from the Williamson synthesis. Then if you take further unsymmetrical ethers, best yields can be obtained by unsymmetrical ethers when you are taking alkyl halides as primary alkyl halides. You should take here like this, and you should take the uh, tertiary alkoxides. Here you are taking the alkoxides as tertiary because this carbon is tertiary carbon. Sodium tertiary butoxide you have taken, and we have treated with the primary alkyl halide to give rise to. Simply remove this NaBr. NaBr is lost. So what is left over? You write down as it is: C, CH3, 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 C, CH3, 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 O, and Na is lost now, Br is lost. So remaining is what? CH2, CH3, CH2, CH3. So tertiary, this tertiary total group is butyl. This is your ethyl group, na? Ether functional group. So in that way, we can get the best yields of unsymmetrical ethers when you're taking the primary alkyl halide and tertiary alkoxides. Alkoxide should be tertiary. If this is reversed, if primary alkyl halides, instead of primary alkyl halides, if you are taking tertiary alkyl halides and primary alkoxides, what are the products? Let us see here. See here. We can see here, if tertiary alkyl halide is treated with sodium alkoxide to form an alkene, no ether will be formed. See here. Here, instead of alkoxide ONA, I have taken here bromine. Bromine means alkyl halide, tertiary alkyl halide we have taken, and NaOCH3, primary alkoxide we have taken. So remove the NaBr and CH3O, it will react with one of the hydrogen of this methyl group to form CH3OH alcohol you'll get, and remaining CH2, it will form the double bond here. Okay, so that's why you are getting 2-methyl propane, remaining CH3 groups as it is. So that means here, if you're taking tertiary alkyl halide for the preparation of unsymmetrical ethers, means you'll get the alkenes, you'll not get the ethers. That's why we should take primary alkyl halides. Understood, ma? So that is the reason for the Williamson synthesis. This is very, very important VSAQ question and also very, very important for your IP point of view, ma. Okay, ma. So with this, today we have concluded ethers, ma. So tomorrow we'll start with aldehydes, ketones, ma. Okay, ma. Sir, please end the class.